We're on to set builder notation. So set builder notation is a way for us to formally represent the domain and range of a function, okay? When you are using set builder notation, there are key parts to the function. You have your braces. You have your such that. And then you're stating your restriction or your allowance. So what this is telling me, x such that x does not equal 1, which means that x can equal anything but 1. Okay, this is telling me y such that y is greater than 1, but less than 5. Okay. How do you feel about being able to write in set notation? Okay, let's dive in a little deeper. So there are different formats for our textbook. We mainly stick with the such that. Now, for some older textbooks, they use the colon. But as you can see, it still means the same thing. But it's just showing you that there is more than one way that it may not have. All right, so here we're going to evaluate the function and determine its domain. So we have x over x minus 1. First, we're going to practice evaluating from function notation. So evaluating from function notation means that when x is replaced with a value, I'm going to replace x in the equation with that value, in the function with that value, correct? Mm-hmm. So our first one we have is f of 2. So if I have f of 2, that means it now is going to become 2 over 2 minus 1, which equals 2 over 1, which is 2. Agreed? Okay. If I have f of 1, that equals 1 over 1 minus 1, which equals 1 over 0. What does that mean? It does not. Okay. You can't have a 0 in the denominator because there's nothing times 0 is going to give you 1. So this is an example of being undefined. Okay. Things you need to recall about 0 rules. It is okay for 0 to be in the numerator, but it is a no-go for 0 to be in the denominator. Okay, that creates an undefined situation. What that means is that it creates a problem of a value I cannot equal, right? So that means that can x equal 1 then? No, because it's undefined, x cannot equal 1. Okay, what are your examples about 2a? What are your questions? I'm sorry. We're going to do f of a plus 1. Yes. Can you also evaluate non-numerical values? Why, yes, you can. I'm glad you asked. Okay. So what this is saying, where x is, I'm replacing it with a plus 1. So when I do that, I have f of a plus 1 equals a plus 1 over a plus 1 minus 1. This gives me a plus 1 over a. You can also evaluate functions with additional variables. This is going to be important, especially if you plan on going into AP calculus. All right. Okay, so finding the domain, use set builder. So based on what we have, what value did not work for our equation, our function? -1, right? I mean, +1 because it made our denominator equal to 0. So when we write our set, we have, my braces are not the prettiest, by the way, x such that x does not equal 1. And the reason being is that when I plug in 1, what did it do to my denominator? Made it 0. And can you have 0 in the denominator?
No.
No, you cannot. All right, interval notation. I like to call interval notation the lazy notation. Okay, interval notation is simply saying, where did you begin and where did you end? Okay, for interval notation, you're either using parentheses or brackets. It is typically used when you're on a number line, but it also can be used in an XY coordinate plane. And if it's infinite, goes on forever, then we use the infinity symbol. This is like one of the first things we learned in Algebra 2, by the way. Okay, so here, for example, I have this number line. It starts at -1 and makes its way to 3. Because the circles are closed, I use brackets. The circles are closed where it starts and where it ends. That means that there's no discontinuity. There's nothing preventing my graph, my table from having all those points defined. Okay, here we have open circles, and because they're open circles, we use parentheses. And that's because it means that the values are not included. Everything in between there is included, but are those in beginning and end values included? No, they're not. Okay. Now, what if I am going on forever? So notice here, this one, it goes forever to the left, and the value that's forever to the left is -infinity. So when I read this from left to right, it starts at -infinity, but it ends where? At 3. And infinities are always going to be parentheses. And this is a bracket because it is closed. Okay, you can't contain infinity, so it can't be included in your values because you can't stop infinity. Okay, when you're going forever to the right, that is positive infinity, right? So when I read from left to right, because that's how we read, I start at 2 and it's an open circle, so it's parentheses, and I end at infinity, so it's parentheses because you cannot contain infinity. All right, let's do some examples. All right, so it says find the domain and range of G, use interval notation. Your domain is from left to right. Your range is from bottom to top. Okay, so from left to right, what is happening? Well, from left to right, I'm going forever to -infinity and forever to positive infinity. So my domain is from -infinity to positive infinity. Yes. My range is from bottom to top. What is the lowest value that I'm at? -1, and it's a point there, so it's included. And then where do I keep going? To infinity, to positive infinity. So that's your domain and range. Why is it my range positive? Because going up is positive wise. Okay, next, evaluating from a graph. So if I have G of -1, that means I go to -1 on the x-axis. I'm going to follow it up to the graph. And at the graph, I'm at what? 3. So G of -1 equals 3. Okay, that's using the graph. If I was to use the, oh, I did it backwards, my bad. Switch these around. If I was to evaluate using the function, I'm looking for G of -1. That means I have -1 squared minus 2 times -1. That gives me a negative times a negative is a positive. Negative times a negative is a positive. And what do I get? So whether I'm solving it symbolically with the equation or visually with the graph, I still got the answer of 3. What are your questions about evaluating symbolically and graphically and stating the domain and range? Okay, again, domain, left to right, range, bottom to top. Okay, we're gonna do another one. So if I want to evaluate f of 1, well, when I try to evaluate f of 1 using the graph, what do you notice? Is there an f of 1? No. So what does that tell me about f of 1? It doesn't exist. It's undefined. That's not how you spell undefined. It's undefined. The reason why it's undefined is because square roots have rules, right? Does anyone remember the rule for a square root? No negatives. Underneath the square root, you can't have any negatives. If I find f of 1 and I have 1 minus 2, what does that produce underneath my square root? A negative 1. So evaluating this for domain and range, my domain is how far left do I go? How far left do I go? I go to 2, right? And then how far right do I go? Infinity. Okay. My range from bottom to top, what is the lowest I go? 0. And what's the highest I go? Infinity. So this is it in interval notation. So when I write it in set notation, my formal way of writing this, I would have my brace x such that x is greater than or equal to 2. And that makes sense because I like to think of this as an arrow and I'm heading where? To infinity, right? Positive infinity. And this one, y such that y is greater than or equal to 0. Questions, comments, concerns about evaluating and domain and range relationships? Cool. All right.